All right, this is our last section of chapter 4, and it's applications, but we have done all of these types of problems before, except for, I think I mentioned yesterday, just one new thing. So I don't expect it to be difficult. Our first objective is to solve a right triangle, and solving a right triangle just means finding all the missing parts. If I give you 2 parts, well, altogether a triangle has 3 angles, 3 sides, 6 parts. But if we're talking about right triangles, then we already know one of the angles. There's only 5 parts left that we're really trying to figure out. If you give me 2 of them, I can find the other 3. Just to have uniform labeling, let's use capital A, B, and C for the angles, and then lowercase a, b, and c for the sides, but label your sides so that little a is opposite angle A, little b is opposite angle B, and c is always your hypotenuse. We just need to be consistent in the way that we're labeling things so we know all what we're talking about. First example, solve the right triangle, round lengths of sides to 2 decimal places and angles to the nearest 1/10 of a degree. So let's just draw that. And my drawings are never going to be to scale, but I'm going to say there's my right angle, there's my hypotenuse. Doesn't matter which angle I call A and which angle I call B, but once I label those, it does matter which side I call little a and which side I call little b. Little a would be opposite angle A, little b would be opposite angle B. And we're given that A is 54.8 degrees. All right. We need to find angle B and little sides A and B. So do you see anything that looks like it would be easiest to find first? Yeah, it'd be easy to find this angle if we know that any triangle has 180 degrees in its interior angles. 90 is already accounted for by this right angle. So angle B is going to be 90 minus 54.8. And that is 35.2. Let me double check that. 89, 90. Yeah, 35.2. So now we have all 3 angles, but only one of the sides. When we're trying to figure out how to calculate A, we just think which trigonometric function would involve the side I do know and the side I'm looking for. Well, I could either use angle A, or now that I know angle B, I could use it. But which trigonometric function, if I'm going to use A, which trigonometric function of 54.8 degrees would involve the thing I'm looking for and the thing I know? The thing I'm looking for right now, if I'm looking for A first, that's the opposite side, and C is your hypotenuse. Which trig function uses opposite and hypotenuse? Yeah, sine. So the sine of 54.8 degrees would be A over C. Now, I always try to get the angle or the variable that I'm solving for in the numerator. Just makes the equation easier to solve. To solve for A here, all I have to do is multiply both sides by 80, and I'd have A is 80 times the sine of 54.8 degrees. And the instructions say round sides to 2 decimal places You can double check this. But yesterday I got 65.37. Punch it on the calculator and that's what you got. Make sure your calculator is in degree mode because that 54.8 is in degree mode. Now, let me give you a rule for if we're working for NASA. If we're working for NASA, we're going to try to always use values that are given to us, not values that we've rounded. Because when we've rounded that value of A, we've introduced a small error. And if you're working for NASA, you don't want any small errors. But if we're not working for NASA, then we could use, now that we know a rounded value of A and C, we could just use the Pythagorean theorem to find B. All right. I'm going to follow the NASA rule here and use the two values that I'm given to find B instead of this value that I've rounded. Which trigonometric function of 54.8 degrees would involve the angle, the side I'm looking for and the side I'm given? Which trig function of 54.8 would use B and C?
Cosine.
B is the adjacent side and C is the hypotenuse. So the cosine of 54.8 degrees would be B over C. Oh, I know C. C is 80. And B would be 80 times the cosine of 54.8 degrees. I punched that yesterday and got 2 decimal places, 46.11. Easy breezy. All right, let's do another one where we're given different information. In part A, we were given an angle and a side. In part B, we're given 2 sides. All right, but we do know it's a right triangle. And so it has a right angle, and opposite that right angle is the hypotenuse, which we're given. And it doesn't matter which angle we call A and which angle we call B, but it does matter that we have A opposite angle A and side B opposite angle B. We know B is 4. What seems like it would be the easiest thing to find first? Yeah, if we know 2 sides of a right triangle, then we don't need trig to find the other side of the right triangle. We can use the Pythagorean theorem for that. So A, if I'm able to solve the Pythagorean theorem in my head now without having to write down A squared plus B squared equals C squared, then A would be the square root of C squared, which is 81, minus B squared, which is 16. A is the square root of 65. Now we could use square root of 65 in some other calculations if we needed to, because we haven't rounded that. It's still an exact answer. But once we get approximately 8.06, we wouldn't want to use 8.06 in any other calculation. A is about 8.06. So we need angle A and angle B. all three sides. So for angle A, which trigonometric function would involve a side that I was given and actually two sides that I was given. I don't want to use A because I've rounded it. Which trig function of this? B is the adjacent side and C is the hypotenuse. So we could say cosine of the angle we're looking for equals adjacent over hypotenuse. Now, how do we find the angle A whose cosine is 4/9?
We use inverse cosine. of-
Who was that? Who's talking? Miss Hallie, was that you? Oh, Miss Emma, what did you say?
I said, would you do the inverse cosine of
Absolutely.
4/9?
A would be the inverse cosine of 4/9. Again, I have my calculator in degree mode because I was asked to round to the nearest tenth of a degree. And when I punched that yesterday, rounded to the nearest tenth, I got 63.6 degrees. Yes, ma'am. We don't know that until section 6.1.
I'm telling you, I was watching the.
Okay. Yeah, everybody else is going, law of sines, what? Yeah, law of sines and law of cosines will be the last two topics we have for the semester, and you can use them to solve triangles that aren't right triangles. You can also use them to solve triangles that are right triangles, but I don't think that would be the easiest way. All right. If we want to find angle B and we're not working for NASA, we can say, well, B would be 90 degrees minus that 63.6. If we are working for NASA, then we could say which trigonometric function of B would involve the 4 and the 9. Four is opposite, 9 is hypotenuse, opposite over hypotenuse is sine. So the sine of B equals 4/9. And that means B would be the inverse sine of 4/9, which I got to be about 26.4 degrees. That is the same thing we would get if we subtracted 63.6 from 90. So to the nearest tenth, it doesn't matter. But if we were working for NASA, we would want that correct to the nearest thousandth, 10,000s, 100,000s. Yes. You don't have to work for NASA when you're doing the test. This is Rome State Community College. I'm so happy if you know what to do. Yeah, we're not working for NASA on the test. All right. So the only difference between what we just did in those two problems and the following three problems is we have to draw the triangle. As a matter of fact, we may not even do one of these because two of them are pretty much identical. 1 and 2 are about the same, and I didn't realize that till last night. Let's just skip to 2. There's something I want to tell you about 2, and then I want to have time to review linear velocity and angular velocity. So number 2, a police helicopter is flying at an altitude of 800 feet. Here's my very best helicopter. Here's the ground. Here's an altitude of 800 feet. A stolen car. This one's exciting. The stolen car is sighted at an angle of depression of 72 degrees. Now tell me what you remember about angle of depression and angle of elevation. There was something you wrote. I gave you a note. It's always, always, always with respect to. Nobody remember? It's always with respect to the horizontal. So if this helicopter pilot is looking down at the stolen car, then the angle of depression is actually with respect to that horizontal. This is what the 72 degrees is. The angle between where he is and the horizontal. But you may remember a little factoid from geometry. It's cool. It's one of the few geometry theorems I actually remember. Do you remember something that says if two parallel lines, that sound familiar? Are cut by a transversal, then you remember what kind of special relationship this angle has to that one? They're called alternate interior angles. And the theorem says alternate interior angles are equivalent. So Ms. Chastity, when you said, I know that that angle of depression is this angle at the end, really only because of that theorem. If that angle of depression is 72 degrees, then this angle of elevation is 72 degrees. There's a pilot looking down at 72 degrees here. There's a car thief looking up at 72 degrees here. All right. Find the distance of the stolen car to the nearest foot from a point directly below the helicopter. Do you see the point directly below the helicopter? Right there. My very best stolen car, right there. And we're looking for this distance because the helicopter is going to radio it into the police. So, which trigonometric function of 72 degrees would involve the side we're looking for and the side we know? All right, we could use tangent and say tangent of 72 degrees equals opposite over adjacent, or we could use cotangent and say cotangent of 72 degrees is adjacent over opposite. Since I don't have a cotangent button on my calculator, I would probably just use tangent. Tangent of 72 degrees is opposite over adjacent. If you can't get the variable that you're solving for in the numerator, then it just takes 2 steps to solve the equation instead of 1. You'd multiply both sides by x to clear out the fractions, and then you divide both sides by tangent of 72 degrees. And I did that yesterday and got, yes, sir. Because your answer would come up upside down, let me show you why. If I took that step, the middle step I didn't write in, would be to multiply both sides by x. That would give me x tangent 72 degrees equals 800. What do you need to divide by? The 800 or the tangent of 72? Yeah. So maybe that middle step would be helpful. Maybe you need to write it down. I skipped it. Is that okay now? Okay, all right. Number 1 was just like that. It was a 200-foot cliff. So instead of 800, that's 200. And the angle is 22.3. That's why I don't want to do 2 at the same time. Number 3, a building that is 250 feet high. Can you draw a building that's 250 feet high? Yeah, you know what mine's going to look like. I am not an artist. There's my building that's 250 feet high. Cast a shadow that is 40 feet long. Where does that belong on the picture? Yeah, where do we see shadows? We see shadows on the ground. And over here somewhere, there's the tip of the shadow. From the point under the building to the tip of the shadow, that's your 40 feet long. We want the angle of elevation to the nearest 10th of the degree of the sun at this time. Where does the sun have to be if the shadow is cast in this direction? Yeah, a little bit behind the building if the shadow's falling this way. So over here we have the sun. And here we have somebody looking up at the sun from the tip of the shadow. The angle of elevation is that angle at which the person's neck is craned to see the top of the building at 250 degrees or 250 feet. So which trigonometric function of theta would involve the 250 and the 40? 250 is opposite, 40 is adjacent. So tangent of theta would be 250 over 40. And so how would I find theta? Inverse tangent of 250 over 40. Oh, I didn't need that theta. Not what I'm taking inverse tangent of. Inverse tangent of 250 over 40. I reduced it to 25 over 4. Get the same answer either way. Inverse tangent of 25 over 4 to the nearest 10th is 80.9 degrees. All right. Any questions? Really, we have done problems like that in other sections. The section, I think 4.2, no, 4.3, we had applications of right triangles. That's all this is, applications of right triangles. But there's one thing that you do have one of these on the test. I wanted you to see one new kind of word problem, and I need to show you something in the book. That's page 639 in the book. If I don't know if you would have had any experience with bearings or not, but bearings are what navigators and surveyors use to describe the location of one point with respect to another. When you give a bearing, you always are saying how far something is from this north-south line. Your north-south line is like your base, and then you say how far you are from that north-south line. This first bearing in the A part, we call that, that is 40 degrees north. I'm sorry, 40 degrees east. East is to the left, or excuse me, east is to the right, west is to the left, just like it is on a map. So this is 40 degrees east of north. And we write that in 40 degrees east. Part B, this is 65 degrees west, because that's to the left of north. And we write that north, 65 degrees west. And the third one is 70 degrees east, because it's to the right of south. And so we write that south 70 degrees east. But you actually read it 70 degrees east of south. I don't know why the east is not written first. These notes down here will help you. Each bearing has 3 parts: a letter, either north or south, a measure of an angle, and a letter either east or west. Let's see if we can, just before we get to a word problem, let's see if we can name these bearings from some point O. All right, from O to A. That's this. First, we have to say whether we're closer to the north line or the south line. Yeah, we're going to measure the distance to the north line. And it's not this 75 because your bearing is always with respect to the vertical line, the north-south line. So if this is 75, what's this? The 2 angles are complementary. So if this is 75, that's 15. And since this line is to the right of the north line, that's east of the north line. That's (15 degrees east to the right of north. All right, what if we were sailing a ship from O to this point B? How many degrees is that from the nearest north-south line? If this is 60, then that has to be 30. We're 30 degrees to the left, which means which direction? West. We're 30 degrees west of north. That's how we write it. It would be a little bit easier for me if you wrote the east or west before the north or south, because that's how we read it. We read it 30 degrees west of north. I kind of wish the N was at the end, but I didn't make it up. All right, from point O to point C. How far are we from the north-south line at point C? Yeah, we're actually given that distance. We don't have to subtract it. We are 80 degrees to the left, which means which direction? West. We are 80 degrees west of the north line or the south line? South line. And one more, from point O to point D, how far are we from the north-south line? This is a 35. That's a 35. So this is 55. And so we are 55 degrees to the right, which means east. 55 degrees east of the south line. Now, before we do a word problem, does anybody need to ask me a question about, I didn't get something about the bearings? It's always with respect to either the north or the south line. Yep. All right, how do we use that in an application? A ship sights a lighthouse directly to the south. So we need a ship and we need a lighthouse. Here's my ship, the very best ship, and a lighthouse that is directly to the south. That's, that's somebody on the ship looking at the lighthouse. And there is a second ship that's 9 miles east of the first. Is east to the left or to the right on a map? Right. So I need to call this ship 1, I suppose, so I can distinguish it from ship 2. And I know that distance is what's 9. Okay. What's important is where you start the bearing. It says the bearing from the second ship means we've got to start here to the lighthouse, which is here. Wherever your bearing is from, imagine a north-south line. And then draw, starting here, draw a line that is 34 degrees west. Does that mean left or right? Left of the south line that you just drew. 34 degrees west of south. Does that mean this interior angle is 34 degrees or this exterior angle is 34 degrees?
The exterior angle.
Here's my south line. So that 34 degrees is this. Yes, yeah. So the interior angle is complementary to that. The interior angle is 56 degrees. It's very important that you always start your bearing at wherever it says the bearing is from. So start your bearing at the second ship to the lighthouse. That bearing is 34 degrees to the left of south. And then you can find that interior angle. And then you can see what we're looking for. How far to the nearest 10th of a mile is the first ship from the lighthouse? That's the guy we're looking for. And here's my right angle. So we know one side, we know one angle, we're looking for this side. We always need to say which trigonometric function of the angle that we know would involve the side we're looking for and a side that we know. Which trig function of 56 degrees would involve the x and the 9? Well, the x is opposite the 56 and the 9 is adjacent to the 56. So yeah, tangent of 56 degrees would be opposite over adjacent. We would clear out the fractions and we'd have the x by itself. So I just need to punch on the calculator 9 times the tangent of 56 degrees. It's darn close to 13.3. What's my units here? Yeah, miles. Yes, sir. Yes, because if we drew a parallel line here, this line parallel to that one, then that 56 would be alternate interior to that 56, and that 34 would be alternate interior to that 34. So if I needed it, yes, you're right. All right, one more. We'll talk about the test for a minute. A ship is 9 miles east and 6 miles south of the harbor. Make sure you draw your picture correctly. You have a harbor. And then 9 miles east of that, which means to the left or to the right? 9 miles. Wait, I may not be seeing that. The ship is east of the harbor, so the ship is to the right of the harbor. And it's 9 miles east and 6 miles south. Now I'm gonna read that again and make sure I have everything labeled correctly. Is my ship 9 miles east of the harbor? Yep. And I could have either drawn that 9 miles here, or I could have drawn it here. It wouldn't matter. Is my ship 6 miles south of the harbor? Yeah, it is. So far, so good. So what bearing should be taken to sail directly to the harbor? Where should I put my north-south line? Am I starting at the harbor or starting at the ship? Start where the ship is and sail directly to the harbor. So the ship is where I want my north-south line. And I'm looking for this bearing right here. My bearing is always with respect to a north-south line. So this is the angle I'm looking for. It's with respect to north. I know that my first letter in the instructions is going to be north, and that makes sense. If the ship is south of the harbor, it's going to have to sail north. But I want to know how much or what the bearing is. So if I call that theta, which trigonometric theta of, or which trigonometric function of theta would involve the 9 and the 6? 9 is opposite, 6 is adjacent. So tangent theta would be 9/6. And theta would be inverse tangent of 9/6, or because I'm a math teacher, I reduced it. Inverse tangent of 3/2 is 56.3 degrees. But I just need to figure out how to write that as the actual bearing the ship should take. Yeah, ship should take. If that's 56.3 degrees, I'm going to radio the captain the bearing. What's it going to be? .3 is the middle part of it. What about the north or south and the east or west? It's with respect to that north line. We said the ship's going to have to sail north if it starts out south of the harbor. Now, what about east or west? It's going to the right of its north-south line. I said, yeah, that's not right. That's left. It's left of its north-south line. So it's 56 degrees, 56.3 degrees west of north. If you'll just start your bearing make sure you start your bearing from the right place. Draw that at the ship, not at the harbor. You'll get that right. Now, let me just add something here, like a part B. What would the ship's return bearing be? Sailing back home at the end of the day, that means we're starting at the harbor and we want to know what this angle would have to be from the harbor. The bearing would be that angle. That is east of the south line. How many degrees east of the south line is the ship going to have to sail? Yeah, it's the same 56.3 degrees, but now it has to sail south to get back home. And to the left of that north-south line is, I'm having trouble with left and right today. That's to the right is east. Because if you were coming home, so this is, you got it now? No, it's okay. The part that was typed starts at the ship and gets to the harbor. At the end of the day is what I'm asking, to come back from the harbor to where the ship originally was.
So it's going back to where. Okay, I thought it meant return, like go back to the harbor. That's why I was confused.
Oh, okay. I could have added something to that question. What would the ship's return bearing be? Return, I could have said to its original position, and that would have helped you, right? Okay. No, it's already at the harbor. It wants to go home. All right. We have 10 minutes. And I'm telling you that the 12 problems on part B look exactly like I said they would look. These first 3 problems are from 4.7. Find an exact value of a trig function. Use a sketch to find the exact value of a composite trig function, and then write a trig function as an algebraic expression. We did those 3 yesterday. And then 2 graphs. No, this is 4 graphs. 2 of them are just basic trig functions that haven't been shifted in any way. And 2 of them are trig functions that have been shifted or reflected. So the very best way to prepare for these 4 problems is to do that blank page I posted in Momentum and send it to me and say, make sure that that's right before I memorize it. All right. And really, you memorize it just by filling out that blank page a couple times, 2 or 3 times. So that's 14 through 20. You don't get a calculator for, because I want to make sure, you know, you can do that without a calculator. You need a calculator for the word problems because I'm not asking for an exact answer. I'm looking for a decimal approximation. These last 3 are what we did. Actually, 21, 23, 24, 25, all 4 of those are like we did today. And then number 22 is linear or angular velocity. And we need to look back at 4.1 real quickly. This is page 2-ish of your 4.1 notes. On the previous page, we had developed these formulas that you listed on the first page of part A. What is your formula for finding the radian measure of theta? Yeah, it's just the arc length divided by the radius of the circle. And then if I wanted a formula to determine the arc length, all I'd have to do is multiply both sides by r, and I'd have S equals r theta. That's your arc length formula. And the one word problem that you had on part A, something about how far did the minute hand travel? That was the arc length. How far does the minute hand go around that circle? What about linear velocity? Know what your variables stand for. What's the linear velocity formula? That's angular velocity. Linear velocity is just distance divided by time. Just like distance equals rate times time, rate equals distance divided by time. Well, the distance is S, how far the minute hand maybe is traveling, divided by time. And then the definition of angular velocity, oops, the variable we used for angular velocity was that omega. That's an amount of rotation divided by time. And then the last formula was express linear velocity in terms of angular velocity. And all we did for that is say, well, in this linear velocity formula, I could say S is r times theta. And that theta over t is your angular velocity. So velocity is r times omega. All right. If you understand the variables, if you understand that this is just distance divided by time, and this is an angle divided by time, then you can get all those formulas easily. Now, number 3 on this page is pretty much what the problem on part A was. Through how many degrees does the minute hand travel? No, it wasn't. We were looking for an arc length there. Yeah, it was like number 4. That was the problem that was like the one on part A. You were looking for a distance a minute hand had moved. You have one problem on part B of the test, number 22. It has 2 parts. One of the parts is looking for a linear velocity. One of the parts is looking for an angular velocity. So the one that's looking for angular velocity is a lot like this. You have a nail embedded in a tire. A tire is rotating at 14 revolutions per second. You want the angular speed. Well, the symbol for angular speed is omega. And omega is an angle divided by time. If this wheel is turning at 14 revolutions per second, then you write that as 14 revolutions over 1 second. But if you want it in radians per second, use your unit canceling. If you want to change revolutions to radians, you need to write a unit fraction, a fraction that equals 1, that has revolutions in the denominator and radians in the numerator. Those revolutions cancel and leave you radians per second, which is what you were asked for. So just 28 pi. 28 pi radians per second. And then the problem that asks for linear velocity is a lot like this number 5. The linear velocity is the radius times the angular velocity. You have to be given a radius. The radius, the distance from the center of the Earth to the satellite was 4,500 miles. And the satellite makes 1 revolution every 90 minutes. So 4,500 miles is your radius. Your omega is 1 revolution in 90 minutes, but you just need to change that to miles per hour. So in this problem, it took me 2 unit fractions to get miles per, or revolutions per minute into miles per hour. I'd say look back at 41 and look at all 4 of those problems, but the part A and part B on the test are most like number 1 and number 5. All right, we cut the test in half so that you could do this half in an hour. So we'll start at 8:30 and finish at 9:30 tomorrow, and then we'll be on to chapter 5. If you want to complete this sheet and send it to me, I'll check it to make sure you have everything you need to know about the graphs of the trig functions correct before you really hunker down to memorize it. All right, see you tomorrow. Email me anytime tonight if you need me.